ever think about just the amount of data companies, like internet companies, are dealing with these days?
It's unbelievable.
It's mind-boggling. Like when you think about Facebook gathering 6 terabytes of user activity every single day.
Every day.
Yeah, that's like the entire Library of Congress daily.
It's really hard to even fathom that amount of data.
It is, and it's not just for analysis anymore. This data is fueling real-time features that we're using all the time.
Yeah,
Recommendations, search results, even security features to protect us from spam.
absolutely.
Handling this fire hose of information is a huge technical challenge.
It really is.
And that's where Kafka comes in.
It is indeed.
So today we are doing a deep dive into Kafka based on the sources that you've provided, excerpts from the original research paper, and a summary article.
Right.
To uncover how the system developed at LinkedIn has become so essential for companies that are dealing with these massive data streams.
It's a fascinating story.
It is. So we're going to explore how Kafka works, the clever choices that make it so efficient, and how it differs from traditional messaging systems.
Sounds good.
So let's start with those traditional systems.
Okay.
What were the limitations they faced in this new world of big data?
Well, traditional systems were really designed with different priorities in mind.
Okay.
Um, Imagine like a bank processing transactions
Right.
or an online store managing orders in those situations. Reliability is absolutely paramount.
Right. Every message has to go through.
Every message has to be delivered once and in the correct order without fail.
Yeah.
But when you're dealing with log data, the occasional dropped message isn't a catastrophe.
Right.
Speed becomes the priority.
So it's a trade-off reliability for speed.
Exactly.
Yeah.
And those older systems just weren't designed for the scale and distributed nature of data storage that modern internet companies require.
Right. They struggle to keep up.
They struggle to keep up with the sheer volume.
Yeah. So Kafka comes in with a fresh perspective.
Right.
Your sources describe it as combining the simplicity of writing to a log file with the power needed for the internet age.
Yes.
Can you elaborate on that?
Sure. Imagine a system as simple as writing to a log file, but built for the scale of the internet. That's Kafka's core.
Okay.
Each topic, think the user activity system metrics,
Okay.
is essentially a stream of messages, like a dedicated log file for each type of data.
Okay.
Producers write to these topics, consumers read from them, and it all happens incredibly fast.
That makes sense. So how does it actually achieve this speed? What's happening under the hood?
Well, one key difference is how Kafka handles messages.
Okay.
Instead of using complex message IDs like traditional systems,
Right.
it uses a simple offset in the log.
Okay.
This eliminates the need for complex indexing, which really speeds things up.
Interesting. So no more messing around with indexing, just pure speed.
Right.
But what about efficiency in other areas?
Kafka is obsessed with efficiency at every level.
Okay.
For example, storage is handled using simple segment files instead of a fancy database. It's all about maximizing raw performance data transfer is done in large batches of messages, which minimizes the overhead from constantly communicating with the network.
Okay.
Think of it like sending a care package instead of individual letters.
Right.
It's much more efficient.
Okay, that's a helpful analogy.
Good.
But wouldn't using simple storage mechanisms like that make it harder to track which messages have been read by consumers?
That's right. It does introduce that challenge because Kafka doesn't track consumption on the broker itself.
Yeah.
Deleting messages becomes tricky.
So how does Kafka handle that?
The solution is quite clever, actually. Kafka uses time-based deletion.
Okay.
Messages are kept for a predetermined period, say 7 days, and then poof, they vanish.
Oh.
This works remarkably well in practice, especially since most consumers are processing data either in real time or at regular intervals.
I see. So by not tracking who's read what on the broker itself,
Right.
Kafka gains a performance advantage, but it relies on this time-based deletion to manage storage. That makes sense, but hold on. If messages just disappear after a certain time, what happens if a consumer needs to revisit older data? Let's say they need to fix an error or rebuild an index. Does that create problems?
Actually, no. In fact, this time-based deletion opens up a pretty interesting possibility, rewinding,
Okay.
because consumption isn't tracked on the brokers. Consumers can actually go back and reread those older messages. It's a unique feature that traditional systems with their focus on strict message delivery guarantees don't offer.
That's fascinating. It's almost like having a time machine for your data, isn't it?
You could say that.
You can rewind and replay events.
It's a very powerful capability. But what's really intriguing is how this seemingly simple concept of a log file, combined with some clever engineering, has revolutionized how companies handle massive data streams.
Let's talk about that. Can you give us an example of how a company like LinkedIn, where Kafka was born, actually uses it?
Sure. LinkedIn uses Kafka to manage virtually every aspect of their data operations.
Oh, okay.
We're talking user activity system metrics, even auditing, to ensure that no data is lost. In fact, they have multiple Kafka clusters dedicated to different tasks.
Wow.
Some handle real-time applications, while others replicate data for offline analysis in Hadoop.
Hadoop.
Right, it's a framework designed for processing and analyzing very large data sets in a distributed computing environment.
Okay.
It's often used for tasks like data mining and machine learning.
Okay, thanks for clarifying. So Kafka feeds data into these Hadoop clusters for more in-depth analysis.
That's right.
But back to LinkedIn, this flexibility you're describing, handling both real-time dashboards and massive data warehouses,
Yes.
is what makes Kafka so powerful, wouldn't you say?
Absolutely, and this ability to handle such a wide range of tasks so efficiently is what sets it apart from the competition.
Speaking of competition, your sources mention a performance comparison between Kafka and those traditional messaging systems we talked about earlier, specifically ActiveMQ and RabbitMQ. They were challenged to write and then read 10 million messages as fast as possible. What were the results?
Kafka absolutely blew them away. It was several times faster at writing those messages, and even more so when it came to reading them.
Wow, that's quite a performance gap. Why such a dramatic difference?
It's a combination of factors.
Mm.
Part of it is Kafka's relentless focus on speed and its incredibly lean design. It simply has less overhead compared to those older systems.
It's like comparing a streamlined race car to a trusty but lumbering truck. Both have their uses, but when it comes to pure speed,
Right.
the race car wins every time.
Precisely.
Right.
And that's what makes Kafka so compelling. But beyond speed, what's truly remarkable is how Kafka leverages the power of distributed systems to achieve this level of performance.
That sounds like a perfect segue into the next part of our deep dive. Let's explore how Kafka distributes its workload and manages to handle these massive data volumes without breaking a sweat.
So you're probably wondering how Kafka manages to spread the work and handle these massive volumes of data. That's where its distributed nature comes in.
Okay, bring on the details. I'm especially curious about how Kafka avoids having a single point of failure, that central brain that could bring everything crashing down if it goes offline.
That's where things get really clever. Instead of a single master node, Kafka relies on a distributed system called Zookeeper.
Zookeeper, huh? That's a new one. What is it exactly?
Think of Zookeeper as a kind of coordination service for distributed systems. It's like a shared directory where different parts of the system can store and retrieve information about each other. For example, Kafka brokers, the servers that handle the data, register themselves in Zookeeper so other components know where to find them.
So it's like a phone book for the Kafka cluster.
Exactly, and not just for brokers' consumers. The applications reading data from Kafka also use Zookeepers to coordinate their activities. They team up in what are called consumer groups, with each group responsible for consuming messages from specific topics.
Okay, so consumer groups are like teams of consumers working together, but if you have multiple consumers in a group all reading from the same topic, wouldn't that create duplicates?
That's a great question. That's where Kafka's concept of partitions comes into play. Think of each topic as being split into multiple partitions, like slicing a pizza.
Okay.
Each partition is consumed by only one consumer within a group. So while multiple consumers in a group might be reading from the same topic, they're each working on their own separate partition.
Ah, I see. So no duplicates, just efficient parallel processing. This partitioning idea is crucial for scaling up, right?
Absolutely. It allows Kafka to handle enormous volumes of data because each consumer only needs to focus on its assigned partition. But there's another layer to this. What happens when a new consumer joins the group or a broker goes down?
Things get messy, I imagine.
Not at all. Kafka has a process called rebalancing, triggered when a consumer joins or leaves a group, or if a broker fails. This process uses Zookeeper to coordinate and reassign partitions among the remaining consumers.
So it's like the system dynamically adjusts to ensure that the workload remains balanced. Even when things change, consumers can come and go, brokers can go offline, but the data keeps flowing.
Exactly, and this rebalance process is designed to be very efficient and minimize disruptions, even with many consumers and partitions. But remember all this talk about brokers, partitions, consumer groups, it can make Kafka sound complex. You might think you need to be a distributed systems expert to work with it.
I admit it's a lot to take in, but how difficult is it to actually use Kafka from a developer's perspective?
Well, the good news is that Kafka's API is surprisingly simple, especially considering the sophisticated tasks it's performing behind the scenes. Producers and consumers interact with Kafka using a straightforward messaging paradigm.
So developers don't need a PhD in distributed systems to harness the power of Kafka.
Not at all. Kafka abstracts away a lot of the complexities, letting developers focus on building their applications without getting bogged down in low-level infrastructure details.
That's reassuring to hear now. Earlier, we talked about Kafka making some unconventional choices to achieve its incredible performance. Could you give us some specific examples?
Absolutely. One key decision was relying on the operating system's page cache instead of building a custom in-memory caching system.
So Kafka's taking advantage of the operating system's built-in memory management rather than reinventing the wheel.
Exactly. This avoids unnecessary data copying and lets Kafka leverage the operating system's highly optimized caching strategies. It also keeps Kafka's memory footprint relatively small, even when handling massive data sets.
Smart. What other tricks does Kafka have up its sleeve?
Another clever optimization is the use of the send file system call.
Okay.
This allows Kafka to transfer data directly from the disk to the network socket, bypassing the usual kernel buffers and minimizing the number of times data has to be copied.
So it's like a super efficient data pipeline, streamlining the flow of information from storage to the network.
Precisely, these optimizations, while seemingly small on their own, add up to make a big difference in Kafka's performance, especially when dealing with the huge data volumes common in modern applications.
Okay. We've covered how Kafka combines the simplicity of log files with the power of distributed systems, but let's shift gears a bit and talk about real-time applications. You mentioned earlier that this is where Kafka really shines. How does it handle the need for low-latency data delivery?
That's where Kafka's pull-based consumption model comes in. Instead of pushing data to consumers on a schedule, consumers can actively pull or fetch messages as soon as they become available.
So it's like having a live feed of data instead of having to wait for periodic updates.
Exactly. This makes Kafka perfect for applications that demand immediate access to the latest information, like real-time dashboards, monitoring systems, and even things like fraud detection.
It all starts to come together now, scalability, speed, and
Mhm.
this real-time capability. It really makes Kafka a versatile tool. But before we get too carried away, can you remind us about those guarantees around message delivery? You mentioned earlier that Kafka makes some trade-offs in this area.
Right. Kafka generally aims for at least once delivery. This means that in certain situations, a message might be delivered more than once.
So it prioritizes speed and efficiency over the absolute guarantee of delivering each message exactly once. But wouldn't that create problems? Imagine a banking system processing transactions. That would be a nightmare.
You're absolutely right. For certain applications, that's unacceptable. But for many applications that use log data, the occasional duplicate message isn't a big deal. And if an application absolutely requires stricter guarantees, it can implement its own deduplication logic using unique message keys or offsets.
Makes sense. So we've covered Kafka's architecture performance tricks and how it handles message delivery. But what about data integrity? How does Kafka ensure that data is protected from corruption and loss?
Kafka has multiple safeguards in place. For instance, each message is stored with a CRC checksum, which allows Kafka to detect and discard any messages that have been corrupted during storage or transmission.
It's like a built-in safety net, catching any bad data before it can cause problems.
Exactly. Kafka even has a recovery process that automatically removes messages with inconsistent checksums. This prevents corrupted data from spreading through the system.
That's reassuring. But what about situations where a broker, one of those servers in the cluster, fails completely? What happens to the data stored on that broker?
That's a good question. In the current version of Kafka, if a broker fails, any messages stored on it that haven't been consumed become unavailable until the broker is restored.
So there's a risk of temporary data loss in case of a broker failure.
Yes, that's a limitation in the current version. However, the authors of the research paper you provided mentioned plans to add built-in replication in the future. This means each message would be stored on multiple brokers, providing redundancy and ensuring data remains available even if one broker goes down.
That sounds like a major step forward. Replicating data across multiple brokers would definitely enhance Kafka's reliability for mission-critical applications where any data loss is simply not an option.
Absolutely. It's a natural evolution for Kafka, making it even more robust and resilient. But there's another exciting development mentioned in the paper that we haven't touched on yet.
Oh, do tell.
The authors hint at the possibility of adding stream processing capabilities to Kafka in the future.
Now that sounds intriguing. What exactly does that mean and what kind of potential does it hold?
That's a great question, and it leads us to some really exciting possibilities. But I think we need to save that discussion for the final part of our deep dive.
You're right. We've already covered a lot of ground. So for now, let's take a moment to digest all this information and then dive into the future of Kafka and its potential to reshape the world of data processing in our final segment. All right, we've explored how Kafka handles these massive data streams with incredible speed and efficiency. Now let's talk about the future. You mentioned stream processing capabilities being added to Kafka. What exactly does that mean, and how would that change things?
Well, imagine being able to perform real-time computations on those data streams flowing through Kafka.
Okay.
Instead of just transporting data, you could do things like aggregations, filtering, joining data from multiple streams, even applying machine learning models on the fly.
Wow, so Kafka could become like a platform for real-time processing and analysis, not just a messaging system.
Exactly.
What would that look like in practice?
Well, the research paper you provided offers some initial ideas.
Okay.
For example, imagine semantically partitioning messages based on certain keys.
Okay.
This would ensure that related data ends up on the same consumer, enabling distributed stream processing across a cluster of machines.
Okay, I think I'm starting to see the potential here. Instead of just dumping data into a data warehouse for later analysis, you could extract insights and make decisions in real time.
Precisely.
What kind of applications could this enable?
Well, the possibilities are vast. Think about fraud detection as transactions flow through Kafka. You could have a stream processing application analyzing them in real time, flagging suspicious activity immediately.
Oh, wow.
Or consider anomaly detection and system metrics. You could have a system continuously monitoring performance data and alerting you to potential issues before they cause major problems.
It's like turning Kafka into a real-time decision-making engine.
Yes,
That's incredibly powerful, but wouldn't this add a lot of complexity for developers?
that's a valid concern. However, the goal would be to integrate stream processing seamlessly into Kafka, abstracting away much of the complexity.
Okay.
Developers could focus on defining the logic of their stream processing applications without worrying about the underlying infrastructure.
So instead of just transporting data, Kafka could become the central nervous system for real-time data-driven applications.
It's a pretty compelling vision.
It is. And with Kafka's ability to rewind and replay data streams,
Right.
you could even analyze past events and simulate different scenarios. This could lead to better decision-making and more robust applications.
Absolutely.
So we've gone from handling data fire hoses to real-time decision-making engines to time machines for data.
It's quite a journey.
It's amazing to see how a system designed for a specific problem at LinkedIn has evolved into something so versatile and powerful.
It's a testament to the power of simple yet elegant design principles, like the log-based architecture, and focus on efficiency. And as the volume and velocity of data continue to increase, Kafka is poised to play an even more critical role in the world of data processing.
As we wrap up this deep dive into Kafka based on your provided sources,
Hmm.
what's the key takeaway you want our listeners to walk away with?
Well, I think the key takeaway is that Kafka isn't just about handling big data. It's about unlocking the potential of data in motion. It's about making sense of this constant stream of information flowing through our digital world and using it to build smarter, more responsive, and more adaptable applications.
Well said. I think it's safe to say that Kafka is a lot more than just a messaging system. It's a fundamental building block for the future of data-driven applications. So we encourage you to continue exploring these ideas. What new applications can you envision being built on a foundation of real-time data streams? How will Kafka shape the future of decision-making and automation? These are questions worth pondering as we navigate the ever-evolving landscape of the data-driven world. Until next time, keep exploring, keep learning, keep diving deep.